Thank you, Dave. So I'll be talking about optimizing neural networks using structured probabilistic models of the gradient computation. And this represents joint work with James Martins, Rustal Kutanov, and Jimmy Baugh. So despite a lot of advances in optimization over the past few decades, typically when we train a large neural net, we still use stochastic gradient descent, or some variant thereof. And it tends to work reasonably well. We can usually train our networks, but it has this problem, which is that SGD is a first-order optimizer, meaning it only uses gradient information, not curvature information. And first-order optimizers have well-known problems when the curvature is badly conditioned. So you have some directions which have much higher curvature than others. It'll oscillate in those directions and make very slow progress in the directions of low curvature. And so why does this happen? So why do we get these elongated optimization objectives? So the basic reason is that so neural nets represent functions, mapping inputs to outputs. And so when we train a neural net, we're optimizing over a really complicated manifold of functions. But we can't optimize directly on the manifold. We need to represent the network in terms of parameters, like weights and biases. And so when we do that, we're basically mapping a manifold to some sort of flat representation. And as you know from thinking about maps of the Earth, whenever you map a manifold to a flat representation, you introduce some sort of distortion. It'll stretch some things out. It'll distort distances. And so when we do gradient descent to train the parameters of a neural net, we're doing steepest descent in Euclidean distance in flat representation. And that's not a very meaningful distance metric. And so the idea behind an algorithm called natural gradient, this is a classic algorithm for machine learning, but the idea is that we'd like to do optimization on the globe rather than on a map of the Earth. And so what does this mean exactly? So we can measure the distance between two different neural nets in terms of the distance between the functions they compute. So if we assume that the neural net represents a probabilistic model, then given an input, like an image, say, it'll predict a distribution over the outputs, such as the set of object categories that could be present in that image. And so we can measure the distance between two different neural nets in terms of the average KL divergence between their predictive distributions over the outputs. But we can't measure this KL divergence exactly, so we need to approximate it. And so the Fisher information matrix, this is something that you might have seen in a statistics class. So the Fisher information matrix is the second-order Taylor approximation to this average KL divergence. So basically, it's the expectation, if you sample data from the data distribution, of the second derivative of the KL divergence between the predictive distributions with respect to the parameters. And so what this means visually is that we can, if we have networks defined by two different parameterizations, theta and theta prime, then the average KL divergence between their predictive distributions can be approximated with a quadratic, where the quadratic form is the Fisher information matrix. And so that's why Fisher information is useful. And when you actually compute the second derivatives, this will give you the formula you're probably more familiar with from a statistics class. So the Fisher matrix is defined as the covariance from a particular distribution. So sample the input x from the data distribution, and sample the targets y, not from the training labels, sample them from the model's predictions. And we compute the covariance of the log likelihood derivatives under that distribution. And so that gives the Fisher information matrix. And so what's the idea behind natural gradient? So one way to think about gradient descent on the log likelihood is that it's steepest descent in the Euclidean norm on the space of parameters. And so it's basically the direction which increases the likelihood as fast as possible relative to the Euclidean distance moved. But that's not a very meaningful metric because the Euclidean distance depends on the parameterization. You could come up with a different parameterization of the network that represents the same class of functions. Gradient descent will do something completely different. And so natural gradient is an algorithm that was introduced by Shinichi Amari in 1998, and it's doing steepest descent in the Fisher information metric, a more meaningful metric over the space of neural nets. And so the natural gradient is the steepest descent direction in the Fisher norm. It is the direction which maximizes the likelihood as fast as possible, subject to a constraint on the average KL divergence. And so because the KL divergence is an intrinsic metric between probability distributions, it doesn't depend on the parameterization, the natural gradient is approximately invariant to the parameterization of the model. And so change the parameterization, you get the same updates in terms of the actual functions the networks represent. Okay, so this motivation sounds great, but unfortunately, natural gradient is impractical to apply to large neural nets and large data sets. And the reason is that the dimension of the Fisher matrix F is the number of trainable parameters of the model. And modern neural nets can often have tens of millions of parameters. So for instance, if you have a weight matrix between two layers, each with 1,000 units, then that's already a million parameters just for that one layer for a relatively modest number of units. And so we can't store a dense million by million matrix explicitly, let alone compute the inverse of it. And so if you want to apply second-order optimization, you need to make some approximations. And so there are some common strategies that people adopt. The first one is to use a cheap approximation to the Fisher matrix, most commonly a diagonal approximation. And so this is the idea behind several commonly used optimization algorithms, things like AdaGrad, RMSProp, and Atom. And these algorithms involve very little overhead because you only have to store a diagonal matrix. That's very cheap. It's linear. And you can easily invert a diagonal matrix, just invert the diagonal entries. And so these algorithms are very commonly used, and they help a bit. But unfortunately, they're often not that much faster than plain SGD. Another approach that people sometimes adopt is iterative approximations. So rather than explicitly solving a huge linear system, you can approximately solve it with an iterative method, like conjugate gradients. And there are techniques for doing this that don't actually require constructing the full matrix. And so these methods have actually been applied to pretty non-trivial neural nets, but they're very expensive because each time you want to update the weights of your network, you need to run this iterative procedure, which could involve 30 steps, each of which is about as expensive as an SGD update. So iterative methods are very expensive. It's not always clear if they're worth the extra computational cost. And finally, there have been some subspace-based methods that have been proposed. And so you might represent second-order curvature information on a restricted subspace of the space of parameters. And it might naively sound good to, if you only have to represent a rank 20 approximation to the Fisher matrix, but unfortunately, in a high-dimensional space, even a rank 20 approximation is very expensive. It requires storing 20 copies of all the parameters. So those can be very memory-intensive. And so I want to take a different approach. So rather than using a diagonal approximation to the Fisher matrix, I want to come up with a more structured approximation. Yes? So it really depends how you measure that in terms of how fast can they get very close to the optimum versus how fast can they converge to a reasonable solution. So it's kind of a complicated question. Yeah. So I'll take a different strategy and try to come up with tractable approximations to the Fisher matrix. And I don't want to just use diagonal approximations. I want to use something more structured, which can represent the matrix more accurately. And so recall that the Fisher matrix is the covariance matrix of the log likelihood derivatives. And so we can think of this conceptually, like if we draw samples of the gradient. So here's the cost function, and the samples, the gradient will be large in the directions of high curvature and small in the directions of low curvature. So we draw samples of the gradient, and we try to model its distribution. And so if we can fit the covariance matrix to this distribution, then that's the Fisher matrix. But we can't do this exactly. But fortunately, in machine learning, we've spent decades trying to come up with techniques for tractably modeling large distributions in ways that we can actually compute with. And so I want to take advantage of what we've learned about probabilistic modeling and use it to approximate the Fisher matrix. And so it's a fairly unusual probabilistic modeling problem, because normally we try to model data. But here we're actually trying to fit a probabilistic model to a computational process, basically the algorithm that computes the derivatives using backpropagation. And so the Fisher matrix could be 1,000,000 by 1,000,000 or even larger. And so what we want is a probabilistic model such that the distribution can be compactly represented. We don't want to represent a 1,000,000 by 1,000,000 matrix, but we also want we want F inverse to be efficiently computable. And so the strategy that I'll adopt is to impose conditional independence structure based on two things. First, the structure of the computation graph, the graph of which quantities are computed as a function of which other quantities, and also empirical observations about the distribution of derivatives. And so we can make use of what we already know about probabilistic graphical models. Okay, and so if we want to think about the distribution over log likelihood derivatives, we can look at the computation graph for how the derivatives get computed. And so if we're training a deep neural net to do object classification, the backpropagation algorithm for computing the derivatives will start with the forwards pass, where you compute the activations of all the layers of the network. So start with your inputs, compute the first layer activations, second layer activations, and so on, up to the predictive distribution y hat, so that will be its distribution over categories. And then we get the label, so maybe it's actually a dog, and then we backpropagate the errors for all the activations. So the log likelihood derivatives with respect to the predictions, with respect to the last layer's activations, and so on. And actually, just as a technicality, the distribution we're sampling from doesn't draw the labels from the training data, it samples them from the model's predictions. That's fairly important for the definition of natural gradient. And the last step is we compute the gradients with respect to the parameters of the model. And there's an update rule for the parameters, which depends on both the previous layer's activations and the next layer's activation derivatives. And so here's the computation graph for computing the parameter derivatives. And so when we model the Fisher matrix, we'd like to model the covariance over those guys. And so this is a fairly complicated distribution. And so I want to quickly mention an algorithm that I published with James Martins a couple years ago. And so this is what we can do in the case of a fully connected neural net, basically a multi-layer perceptron. So if we take the computation graph that I just showed you, and we impose two independence assumptions. So first of all, we assume that there are no correlations between the gradients in different layers. This assumption actually is empirically false, and we came up with ways to actually model between layer correlations. And somehow it didn't seem to help that much. And so we'll just make the simplifying assumption that there aren't these correlations between layers. And then we also make the assumption that the activations and the activation gradients are independent. And so if we make these assumptions, then the Fisher information matrix has a very nice form. It's a block diagonal matrix with one block for each layer of the network. But that by itself is not enough, because there could be 1,000,000 parameters for each layer of the network, and we can't store 1,000,000 by 1,000,000 blocks. But combining these assumptions, we actually find something, we actually find a pretty useful form. So each of these blocks decomposes as a Kronecker product of small matrices. And Kronecker product is a very useful structure computationally because it means we can efficiently approximate the computation of the natural gradient. So the inverse Fisher matrix times the Euclidean gradient has this form. We take the gradients with respect to the parameters in each layer, and so the inverse of the Kronecker product is the Kronecker product of the inverses. And so when we apply the Kronecker product structure, we basically get this formula. We're just multiplying by inverses of small matrices on both sides. So this is something we can actually compute fairly efficiently. So that's the case of fully connected networks. Can we extend it to convolutional networks, which is what we apply to most visual processing tasks? So there are various kinds of layers that we have to deal with. So first of all, fully connected layers that we just talked about, pooling layers. So things like max pooling. These layers don't have parameters, and so we don't actually have to worry about them in optimization. There are normalization layers, and these generally have a very small number of parameters. And so we can afford to fit the full Fisher blocks over these layers. And so the difficult ones are the convolution layers. And so this is what I'll actually focus on. And so just as a reminder, the way that convolution layers are defined is that we convolve the previous layer's activations with a set of weights or filters, and then we add biases for particular channels in that layer, and then we pass that through a nonlinear activation function. And so let's continue to make the assumption that there are no correlations between derivatives in different layers, and so we can focus on the parameters for a single layer. And so the way that we compute the derivatives for activations for the weights in a layer is that we take one of the activation feature maps in one layer and the derivative map in the next layer, and we shift them relative to each other, and we compute the dot product of the entries in the region of overlap. And so that computes one of the terms, and we'd like to compute the correlation between all of these different terms. And so in order to do this tractably, we need to make some modeling assumptions. We have to assume that the activations and the derivatives are either independent or jointly Gaussian. So this is the same assumption we made in the fully connected case. We also assume no between-layer correlations, just like the fully connected case. But the other two assumptions are new. So we assume spatial homogeneity. So we assume that the statistics of the activations and of the derivatives are the same everywhere in an image. And that seems kind of reasonable. It's basically the assumption we make when we decide to use convolution and share the weights between all image locations. The other assumption might seem a bit more dubious. So spatially uncorrelated derivatives. So the activation derivatives in one image location are uncorrelated with the derivatives in another image location. But we can measure this empirically. So here we have autocorrelation maps for the error derivatives for various channels in various layers of various networks. And these autocorrelation functions are basically delta functions. And so empirically, there's very weak autocorrelations. On the other hand, if you compute the autocorrelations of the activations in a given layer, they're actually quite strong. And so it's significant algorithmically that we're assuming spatial independence for these guys, but not for these guys. And so when we make these assumptions, we get a similar form to what we derived in the fully connected case. So we get a block diagonal structure for the Fisher information matrix, where each of the blocks is a Kronecker product of small matrices. And so each of the factors in the Kronecker product are statistics that we can estimate from the activations of the network and from the derivatives. And this gives a representation which is comparable in size to the number of weights in the network. So it's a very compact representation. And so the approximate natural gradient is cheap to compute, just like in the fully connected case. It only involves operations on matrices which are comparable in size to the weight matrices. And importantly, there's a very small constant factor overhead compared with stochastic gradient descent in terms of the amount of time to compute each update. So it might be 1.5 times more expensive or twice as expensive, but it's not going to be 30 times more expensive. Okay, so that's basically how we get a tractable update rule that approximates a second order update. So one of the important motivations for natural gradient that I mentioned earlier in the talk is that it's invariant to reparameterization. So if you come up with a different parameterization of your network, as long as it represents the same set of functions, then natural gradient will behave equivalently. And so that's the justification for exact natural gradient, but exact natural gradient is intractable. And so the question is, can we analyze approximate natural gradient in the same way? So in particular, can we show that our approximation is invariant to certain restricted classes of reparameterizations? And so it turns out that there is a class of reparameterizations that is invariant to, in particular, homogeneous pointwise affine transformations. And so what this means is that if we have a part of a network here, so we have a convolution layer followed by a nonlinear activation function followed by another convolution layer. We can take this network and come up with reparameterization by applying a linear transformation to the units in this layer before the activation function is applied, and then apply another linear transformation after it's applied. And then it's possible to transform the weights of the two layers so that the network computes exactly the same function. Okay. So I won't go through the mathematical details of this, but the important thing is that after an SGD update, even though the original networks computed the same functions, after the update, they compute different functions. And so SGD is not invariant, but the KFAC algorithm that I just described to you is invariant in the sense that after the update, both networks will still compute the same functions. And so the training procedure is invariant to this reparameterization. So that's a fairly abstract description, but this includes a number of reparameterizations that we often apply in practice. And so if you have a network with logistic units, you can often do better by replacing them with tanh units. And that turns out to be expressible in this class of transformations. You often want to center your activations to be zero mean and unit variance in each layer, like the commonly used batch norm trick. And sometimes we weighten the images in color space so that they're equal variance in all directions. And so because our training procedure is invariant to all these transformations, then that suggests that it ought to achieve the optimization benefits automatically. And so how well does this work? So we evaluated our optimizer on various deep learning benchmark data sets, and we used previously published network architectures which had already been carefully tuned for the task in order to get SGD to work well. And so it's fairly hard to beat these baselines, but in fact, we can beat SGD by fairly significant margins on both the training set and the test set. So here are plots for CFAR 10 and street view housing numbers to standard benchmark data sets. And we get improvements between factor of 2 and factor of 7, depending exactly how you measure. So anyway, that was all in the setting of training a network on a single GPU. And I want to briefly mention something which I'm currently working on. This is primarily the work of Jimmy Baugh, and this is distributed KFAC, so trying to do approximate natural gradient in a distributed setting. And so just some background on distributed SGD. So if you're trying to train a network on a cluster of GPUs, how can you use parallelism to train the network faster? And so one common solution that people would use is synchronous stochastic gradient descent. So basically, you have a bunch of worker nodes which have access to independent subsets of the data, and they compute the gradients independently on these subsets, and then they get they get sent to the parameter server to be averaged together. And so, synchronous SGD basically lets you efficiently compute SGD updates on large mini batches by distributing the computations out to lots of worker nodes. And so the ability to use large mini batches reduces the variance of the updates, which lets you train more accurately. And so that helps. But unfortunately, with distributed SGD, you get diminishing returns because as you add more workers, curvature, right? So you get rid of the stochasticity, but you still have to worry about the curvature of the cost function. And so no matter how large you make the mini batches, that doesn't help with curvature. And so what Jimmy developed is a distributed version of the algorithm. So what we do is we so basically do the same thing as synchronous SGD. So we have a parameter server that stores the parameters. It sends the parameters to a bunch of worker nodes that compute gradients and send them back to the parameter server to be averaged. But then we can also take the extra computations that are done by the KFAC algorithm. So in particular, aggregating statistics of the activations and the activation derivatives, and computing the inverses of these covariance matrices. And we do that in parallel on a separate set of worker nodes. And so all of the additional computation can be done on a separate set of nodes. And so in effect, if you have unlimited parallel resources, then there's basically no computational overhead compared with standard SGD. And so we can apply this procedure to training a large convolutional network. So training the GoogleNet network, one of the widely used architectures for object recognition. And so what we see here is that so we have training curves. So we have training error shown in the dashed lines, test error shown in solid lines. Training error is actually higher because we use input transformations, so that adds stochasticity. But we have two different parameterizations of the SGD baseline, but if we train using our method, we can do quite a bit faster, about 2.5 times faster in terms of the wall clock time. And we can get similar results with other large convolutional networks. And so returning to the question of how far can we scale this up, right? I mentioned that if you try to train stochastic gradient descent in parallel on a cluster, you get diminishing returns as you increase the mini-batch size. So here we have a plot of the training error as a function of the number of training examples that were visited. And so here we have SGD with mini batches of size 256, 1024, and 2048. And as you increase the mini batch size from 1024 to 2048, you get much less efficiency in terms of the number of examples covered. And so you're not actually going to get a linear speed up as you add more machines. But if you train using distributed KFAC, then you get basically the same performance per example as you go from 256 to 2048. And so this suggests that we ought to be able to scale this up much further. We've been training so far on academic scale resources, but we're trying to see how far we can actually scale this up. And so this suggests there's still a lot of benefit we can get in a distributed setting. Okay. And so to conclude, so I've presented an approximation to natural gradient, which exploits the structure of convolutional nets to get efficient updates, which make good use of curvature information. And so we fit a probabilistic model to the covariance of log likelihood derivatives. And this gives effective updates with only a small constant factor overhead compared with standard SGD. We showed that it's invariant to a broad class of reparameterizations of the network. And it significantly speeds up the training of classification conv nets, including very large-scale networks that are commonly used for object recognition. And there's potential for even larger speedups in a highly data parallel setting. So, thank you.
So I'm thinking on GoogleNet slide. That AI plus DX are not knowledge. You can actually before that AI should be that knowledge.
Right. So right. So in practice, it seems to help, and so how do we reconcile that? And so we suspect it's probably just a matter of the initialization. So remember that the procedure is invariant as long as the networks represent the same set of functions. But when you initialize the network using a random set of weights, if you use batch norm, you're actually initializing to a different function than if you don't use batch norm. And James Martins and Yuja Lee found some evidence that actually a lot of the reason that batch norm helps is just that it finds a better initialization for the network. If you carefully initialize the net without using batch norm, you can still get similar performance. Yeah.
For natural gradient, you said that you use rotation output for back computation. You get a list of not only numbers between 0 and 1.
So the network outputs a distribution over the labels, and we sample the label from that distribution.